Hello. So we have a pretty interesting question here that I've made, and we're gonna analyze it. You can feel free to try out this question as well, but essentially it's a chemistry question that assesses one's conceptual understanding of a hydrate, right? A hydrated substance, right, where you have typically an ionic compound, but there's actually water trapped in the substance, and you can actually establish a mole ratio of water to the ionic substance, right? The definition of of that value n, which in this case is 10, right, is the number of moles of water per mole or unit of that other substance where the water is trapped. So oftentimes you might, in these kinds of questions involving hydrates, you might be given some information and you might be asked to determine the value of n, which in this case we're actually already given to be 10. So you might be asked to determine the value of n. That's one possibility. Another possibility, though, and I think that's what makes this question interesting, is we're given the value of n already, and we have a missing element in this ionic compound, and we actually have to use the information that we're given in order to identify and calculate the atomic mass of that substance, atomic mass of that substance, and to ultimately be able to calculate what that element is itself. So it's a very interesting question. You should definitely take a look at it. But I'm just going to go into some of the solution method, and we can do some analysis of the process as well. So the first thing that we're given, right, is that we have a salt of sodium, right? Sodium Na2XO3. X is the element that we have to find, right? And we find that a sample of that hydrated salt is obtained and then dehydrated. So when the salt was hydrated, right, it weighed 15.883 grams, right, before dehydration. So that's essentially the mass of a certain number of moles of the substance itself, plus the mass of a certain number of moles of water that's trapped within the substance, right? So essentially this is the total mass, 15.883 grams. So now once we've dehydrated the water, right? And there are a lot of laboratory experiments that you can do to conduct this process, but essentially you can take your compound and put it over a Bunsen burner, and then actually drive off the water from the substance and obtain, right, eventually you'll have an almost fully dehydrated sample of the substance, right? But here we're already given, right, that the anhydrous salt weighs 10 grams less than the hydrated salt. So after dehydrate, so basically, right, 15.883 minus 10.0, right, is going to let's add some more significant figures here, equals 5.883 grams of anhydrous salt, right? So this is the dehydrated salt. So essentially what we have now, right, is we've driven off all the water. It's amounted to essentially 10 grams, right? We know now that the water is 10 grams. and we know that the salt itself, right, is of sodium is 5.883 grams, right? So essentially that's the first, just that little bit of interpretation that's so important with these kinds of questions. And now what we have to do, though, we have to find the unknown element x. And one thing that we can recognize and that we have to recognize in this example, right, given that we already have that value of n, the number of water molecules per unit of the salts, right, we can actually establish a mole ratio, right? So 10 moles of H2O per mole of Na. Let me just copy this here. Right? And we can actually, first of all, actually figure out we can't quite figure out the moles of sodium of the salt itself immediately, because we would need to find the molar mass of the substance first, and we don't know that if we have a missing element. But we can find the number of moles of water, right? Because water, right, the molar mass of water is basically 1.01, which is the 1.01 grams per mole is the molar mass of hydrogen, right? Times 2 because of H2O, plus the molar mass of oxygen, which is 15.9994 grams per mole. Right? This is the molar mass of water. It's a very common one, and it's going to amount to 18.02 grams per mole. Right? So that's one step, and it's very important. Now we have that molar mass conversion factor, and what we can use it to do is we can actually now find the number of moles of water, given that there were 10.000 grams of water in the sample. So essentially what you would be doing, right, is you'd find, you take 10.00 grams H2O, and you'd multiply it by 1 mole per 18.02 grams of H2O, right? And that is going to give you 0.55 moles of H2O, right? And that's very important because now, right, we can use the value of N, right, which is 10 in this case, right? We know that there are 10 moles of water per mole of the substance. So essentially if there's a certain number of moles of water, there's 1/10 the moles of the other substance. So we have that conversion factor right here. So essentially then what we would get is 0.0555 moles of Na2XO3. And now, right, rather than use the molar mass of this substance to calculate the number of moles, we already have the moles, we have the mass, and we can use, since we have 2 of the 3 unknowns, we can actually now calculate what the molar mass is. So here is essentially what that calculation would look like. It would be 5.883 grams, right, divided by 0.0555 moles, and this is just of Na2XO3, right? That's essentially the molar mass, and what that simplifies to is just a quick calculation of that. 106 grams per mole. If we just want to be consistent with significant figure, I think, yeah, 106 grams per mole is the molar mass of this substance. Now, one thing to remember, right? We already have all but one of the elements in this compound, right? We have 2 sodiums, right? Let's take the atomic masses and just do that little bit of simple multiplication and addition. We'll take 22.99 grams per mole is the molar mass of sodium, right? We're going to add 15.994 times 3. Just keep this consistent. Yeah. 15.994 multiplied by 3, right? Because there's 3 oxygen atoms in the compound. We know that, right? Plus X, right? There's only one of the element X in the compound, and we know that's going to sum up to 106 grams per mole. And then from here, it's just a bit of simple algebra that we would compute. It would be 22.99 times 2, 45.98, plus 15.994 times 3, which is 47.982. And then plus X equals 106. And by the way, these are it's all grams per mole. And you essentially get when you solve for X, you would get 12.038, right? 12, and X is, of course, the atomic mass of the unknown element. Now, that, while it's not perfectly exact, right, it's very, very close to the atomic mass of carbon, and thus we can conclude that X equal the element X is carbon. So this compound, right, is sodium carbonate decahydrate, right? The formula is Na2CO3. And it's true, you could actually work your way to this conclusion using the polyatomic ions sheet, right? You know that given that the sodium has a +2 charge, you know that the other sort of the non-metal component polyatomic ion is going to be -2 charge. So it's either going to be, I guess, looking at the chart, it's either going to be it's most likely going to be carbonate or sulfite. So you don't have you're almost within the vicinity of being able to guess what that ion is, but this is really the more correct way to approach the problem, and it's a very, very interesting question. Assesses your knowledge and understanding of hydrates, of molar mass, mole ratios, and it does require a good amount of thinking. This was the method that I thought of when I came up with the question, but I'm sure there's some other good methods as well to approach it. And thank you for watching.